Hello, everyone. Thank you to the committee for giving me the chance to present the work of my thesis today, entitled Reliable and Efficient Simulation of Ductile Failure over Long Distances. So the motivation behind the work of my thesis comes from the necessity to simulate the ductile crack initiation and also propagation in the industrial world in order to ensure the equipment safety as the pipeline or power plant, nuclear power plant. We also have we also need to predict the contour and shapes in the context of process manufacturing like sheet folding and sheet cutting. So what we are trying to simulate here is a physical process called ductile failure, which can be described as a three-stage process. So the material initial state can be imagined as a matrix having little inclusion embedded within it. So the first stage, as we apply stretch and pressure into our material, we have void that starts nucleating around this this inclusion, and as we continue applying the pressure, we goes on to the second stage where these voids start to grow, and they continue to do so until the third stage occur where the void starts to coalesce to form micro cracks and at the end macro cracks. In literature, there is different and various approaches to simulate this complex phenomenon. So there is what we call the discontinuous approach, which consists of having computation done on mesh with pre-existing crack and computing the propagation of crack using G integral computations. There is also the local approach to failure based on using continuous damage model having continuous variable describing the degradation state of the material. And we have the third category which is the combination of the two, called the discontinuous approach, which consists of using the continuous local damage approach up into initiation and or only inserting crack onto the sufficiently damaged area. The work of my thesis essentially consists of building onto the thesis of Mediaville and Feld-Payet, which have explored the discontinuous modeling using remeshing techniques um, in order to simulate ductile crack, and building on that, using the results of Davas, also which has succeeded to identify a non-local model experimental successfully. So I will build on that to develop an efficient tool which is adapted to large transformation in order to validate it validate it by confronting it to confronting the simulation result to the experimental results. All the development will be within the ZSET finance element software. I will start by presenting the continuous damage modeling that we'll be using during our computation. So our choice has been none other than the well-known Gerson behavior model, which, as we see here in the yield surface, we introduce a continuous variable f which is the void factor to describe the degradation state of the material. This variable can contain contribution coming from nucleation and also from growth, so it can describe initiation and propagation. The limitation of this model is well known, as it occurs at large deformation states where the solution becomes non-unique, and we can notice this in computations as the mesh dependency of our solution. So as we see here, in a tensile test, we have different global responses for different mesh sizes and orientations. A well-known solution is to use what we call models with internal length. So we need to introduce a new variable to the material to describe the material state, which is the characteristic length which describe the interaction between the defaults in the materials. There is with various ways to do that, and we will be using the non-local implicit gradient operator, which can be explained as the following. So in the finite element, we need to solve a new equation, which is the diffusion equations, in order to, from a state variable, compute its non-local equal. So, and we can tune the band of the regularized variable using the characteristic length. There is different models in the literature, and they depend on the choice of the state variable v. And for different choice, we have different elements that can be developed. So in this part, I will describe how we can achieve the transition from the continuous to the discontinuous modeling. So using the non-local modeling, we can have an independent mesh solution. And the next question will be, where is the singularity in the continuum in the continuous field? So the solution to that is to use the crack tracking algorithm, which consists of having as input the damage variable and giving us the actual geometry of the crack. We will be using the Martin-Rigid algorithm developed by Feld-Payet, as I will be explaining it in 2D and 3D example in a minute. So the algorithm can be presented as the following. So we start from a certain point that can be chosen by the user, or it can be the maximum damage point. So we draw a polar grid, and with a precision, with a delta theta precision, we can evaluate the field, the damage field F, and we can compute its derivative with respect to theta. And the idea here is we are looking for the next local maxima. So this local maxima will be the change of sign in this derivative from positive to negative. So doing that, we can find the next local maxima, and iteratively doing the same procedure with the polar grid and looking for the next local maxima, we can find each the nearest local maxima and continue to do so. As we see here, we can detect the branches. So iteratively, we continue to do so until we obtain the whole corresponding crack path. This can be adapted easily in 3D. So we start from the algorithm can initiate crack, or can start from a crack front, as we see here in black dots. The crack front can be subdivided to different segments. For each segment, we will do the same polar search perpendicularly to the segment, and to evaluate, to find the next crack front. And so we do that iteratively until we obtain, as previously, the same crack path, the crack path corresponding to the damage field. Once we have the geometry of our singularity, we need to represent it in our computation. So our choice has been to explore remeshing techniques because they don't have they don't necessitate a supplementary enriched element as needed by the XM, and they don't result in a mass loss. So our procedure will be coupled to an error indicator in order to govern the remeshing technique. So the idea here is to use the well-known error indicator developed by Zienkiewicz, the ZZ2 error estimator, which can be computed as an incremental norm for the whole mesh. So it gives us the global error, and for each element, as it gives us the local error. So the global error can give us the idea of the time for remeshing, and the local error can, coupled with local criteria, can determine the areas where we need to refine and coarsen our mesh. So it can be presented easily, as we see in the slide here. We start from a mesh, and using the ZZ2 incremental error estimator, we can compute the error states for each element, and using a local criteria, we can produce a new mesh, as we see here, only on the interested zones. So the last ingredient in order to achieve our computation, so we have non-local modeling that gives us an independent damage field from the mesh. The margin rigid algorithm can determine the real geometry of the crack. So the last information is the when of the insertion. So the idea here is to evaluate the damage field on the whole crack surface, and when on all the points they exceed the critical value, we decide to insert the crack into our mesh. So our procedure can be described as a loop. So as a loop, having all the different bricks presented previously, and they can it can be explained as the following. So we start from the CDM in large transformation framework, and using the remeshing procedure coupled to the error estimator, we can know when to remesh if we exceed a threshold set by the user, and if so, we know we can reproduce the new mesh. Parallel to that, the margin rigid algorithm can search for the crack in the computation. If it finds a crack, and the insertion criterion is valid, we decide to insert the crack using our mesh intersection algorithm, and the new mesh will be reproduced. And the last step will be to transfer the current state from the old mesh to the new mesh to resume the next iteration, the next increment of loading or displacement. So I present to you here the same computation that have been conducted by Mediavilla and Feld-Payet using our procedure. So as we can see here, using remeshing techniques, we can have mesh locally refined into the damaged area, and we can initiate crack and follow its propagation from each side of the notch, as we see here. Um, the damage will start from each notch and will propagate until we have the whole crack path, as you see here at the left of the slide in green dots. I have conducted a second computation where I use the GTN model in a non-local implicit. We're using non-local implicit gradient with two local variables, cumulative plasticity and void fraction. So the tensile test will result in a high triaxiality in the center of the specimen, and there we have our maximum damage field. As we see here, the remeshing follows this damage field, and we will have the crack initiate and start to propagate from there. An important point, as we see here, we're using our procedure, we will have only refined mesh in the process zone close to the active crack area, and coarsen mesh in the already broken zones. The same computation onto the notch tensile specimen can be achieved in using 3D mesh. the same simulation can be done. So the damage will be so the damage will be maximum at the center of the specimen, and the crack will initiate there automatically. Mesh will be locally refined into this zone, and it will propagate from there following the damage field as we saw in our procedure until we have the well-known the Capcom crack path. So using our procedure, we can see that we can obtain the same crack path as we notice in experimental tests, which is a strong point in our procedure. And my presentation comes to its end. So in conclusion, ductile crack simulation is a complex problem where we have well-known complex procedure where we have well-known problem, and as you see, we can solve them in our procedure using non-local modeling, mixed non-local elements with remission on current procedure configuration. I didn't bring this point of volumetric locking problem in my presentation, but we have treatments for that, and using our remission technique coupled with incremental error estimator, we can have fine mesh only in the active crack area. So my future work will be focused into producing more complex 3D simulation on more complex structures, and validating the procedure by comparing the global responses of the simulation to their corresponding experimental tests. We can also compare the results of the crack packs from simulations, also to the experimental tests using the same algorithm, but this time applied to images. So thank you for your attention, and your questions are welcomed.